here's an idea. Let's say we have a vector space. So we have some vector space. It's a set of vectors. We have operations, addition, and scalar multiplication. And now we're going to take some of the vectors, so some non-empty subset of the vectors. So V is a vector space. And what I'm going to do is I'm going to take some W, which is a subset of V, and W is not empty. Not empty. So we're going to take at least one vector. We're not going to take nothing. Okay. So under these conditions, when is W a vector space? Well, there's a lot that needs to be checked, right? We have to check for commutativity and associativity of our vector addition, and we have to check for the other funky associativity that doesn't have all the elements being the same, scalars and vectors together, and we have to check for additive identities, and we have to check for additive inverses, right? And we have to check for multiplicative identity with a scalar multiple, 1 times anything is itself, and we have to check also for distributivity. That's a lot, but do we really have to check all those different things? Let's think about it. Okay, so first of all, before we can check any of the rules, I need us to stay inside W, or W is not going to be a vector space. For example, if I have two vectors in W, and let's say I add them, and I'm not in W, well then W is not going to be a vector space. So I need closure. And if I have a vector W and I have a scalar, and I scalar multiply, and that takes me outside of W, then W is not going to be a vector space. So I need these two things first. I need closure. So I need lambda W is in W for any lambda in the field, whatever that field is, and W in W. And what else do I need? Well, I need W1 plus W2 to be in W for any W1 and W2, which are in W. So I need these two things. I need this and this before we can check the rules. But guess what? It's amazing. We don't have to check any of the rules. We get them all for free. So what do you mean? Okay, how do we get the rules for free? Okay, well, let's think about this for a second, right? If I have vectors in W, those vectors are also in V because W is a subset of V. They commute in V, so they still commute because we're adding them using the rules for V. So therefore, we don't have to check commutativity. We don't have to check associativity. We don't have to check the other associativity, the one with the scalars, because all of those things work in V. So because of that, they're still going to work. We don't have to check the distributive law. We don't have to check for the identity multiplying a vector. Those all work. Those rules all work because they work in V. And if we're adding and multiplying vectors that are in W, those vectors are also in V. So what do we have left? Okay, you might say, but wait a second. Some of them are not just sort of simple equals rules. Some of them are things that say something exists. So what we need, you might say, is that we need there to be a zero vector, and we need for every vector in W, we need its inverse to be in W. But let's think about that for a second. You see, if W is in W, and we have these two rules, let's now assume we have these two rules. Let's say these work. Right? Then we already know minus 1W is minus W. And we also know W plus minus W is 0. So if we have this rule, then we get a 0. And if we have this rule, we get the inverse. So we get everything from just these two rules. The only thing we need to check is closure, and all the rules are automatically satisfied. So this is a great thing. In order to check to see whether a subspace is a vector space, we only have to see these two things, and that's really easy. It's a lot easier than checking one by one all of these different vector space axioms. So whenever you have something and you're being asked to show it's a vector space, one of the things you could do is you could ask yourself, okay, is this a subset of something that I already know is a vector space? And if so, then you don't have to show much. All you have to do is show closure. Closure under addition and scalar multiplication. Okay. So let's write this out as a definition. If V is a vector space and W is a subset of V, which is closed under addition and scalar multiplication, so like our two rules up there, okay, so if we have a vector space with a subset that is closed under addition and scalar multiplication, then we call W a subspace. Now, hold up. I've done something that I need to rearrange. You see, I have to make a choice here because we did use something. We used the fact that W was not empty. I said it wasn't empty here. So I have to either write that W is not empty, or I could add a third axiom. So if I don't want to assume that W is not empty, I could introduce this. So if I introduce this as well, then it's a vector space as well. Now, I don't like doing that. I like saying, hey, if V is a vector space and W is not empty, then it's a subspace if it satisfies two rules. It just has to be closed under those two things. The book doesn't like to do that. The book likes to allow the possibility for W to be empty at first, but then say zeros in W. So that's a slight difference in what I would do because it means three rules. So here's what you could do. You could say, okay, if W is a subset and it meets three rules, then it's a vector space. Or you could say if W is a non-empty subset and it meets two rules, it is a subspace. And either of those is fine with me. You're allowed to use either definition, whichever of those two definitions you like. So if we do it this way and we don't say W is not empty, you have to put in a third thing that you have to check. But if you know that W is not empty, then it has some vector W. And then, well, because of scalar multiplication, it has the inverse of W. And because it's closed under addition, you can get the zero. So just assuming that, you don't need to have a third rule. So like I said, I leave it up to you. Your book decides to do it with three rules. I prefer to do it with two rules and just say it's non-empty. They're equivalent. They're the same definition. And that's the definition of subspace. So now we can start looking at some subspaces, some actual examples of subspaces in the next video.